All right, how's everyone doing today? Let's see. Main things I'm planning to do today. Keep in mind, Test 1 season begins next Monday. Again, that will happen during lab time, so that does not mean you have to be ready by 10:30 a.m. on Monday. It happens during lab these 3 days. So my plan for today, Friday 16th, is practice the parts of Chapter 7 that will be on the test, because Chapter 7 is just taking longer than I expected, so I'm just kind of cutting it off here before the end. There's a few more concepts that will go over after the test, but I'm cutting it here. The last thing we talked about was work. The last Chapter 7 concept that will be on the test is work. And I've divided the Chapter 7 homework up into 2 parts. There's the part that's on Test 1 and the part that isn't. It says that on the list of questions and also on the document copy. I'll show what all that looks like momentarily. Today we will practice a few pieces from Chapter 7, just to make sure the last things we talked about make sense. And I will also then show you all of the test review material that is currently on Brightspace and make sure that you know the things that you should be doing before the test next week. And once again, I probably said it 8 million times, the test is during lab next week. So at 1:30 Monday, Tuesday, or Wednesday, you report here. And unlike normal lab, you can choose any one of those 3 times if a different one works for your schedule. Maybe you want to get it over with on Monday, maybe you want the extra time to study. That's up to you. Normal labs, you can't just jump around, but at least for the test you can. And lectures, Monday the 19th and Wednesday the 21st, will be more practice, basically. I'm not going to teach anything new those days. The main focus of those days will be making sure that you guys are comfortable with the test material. If there's anything you encountered while studying or doing the homework or looking over extra practice questions, I want to know on those days. We will cover it all together. With all that said, how are y'all feeling right now? And do you have any questions before we get started today?
So will the test be like the practice test that you posted on Brightspace?
Yes, it'll be similar. Let me load up said practice test to kind of show people. Oh, gotta reload Brightspace. Let me show what that looks like. The practice questions that I uploaded, this is basically just extra practice. The homework is already the practice you should be doing, but I always have students wanting more, so I've posted more. It's within the Test 1 tab. This Test 1 is on chapters 1 through 7. And I have listed in this tab the list of concepts you should be familiar with. If you look over the Chapter 7 notes, there are a few concepts that aren't on this list. Those concepts you haven't covered in class, they won't be on the test yet. We'll cover those after the test. The practice test, or the practice questions, are posted within this tab, and it's formatted a little bit differently to how the actual test will look. On the practice test, I've separated between concept and math questions. First page is lots of rapid-fire concept questions, and then the next couple pages are various math problems, each usually with multiple parts. The formatting will be similar, except the questions will be kind of mixed together. Like one question might have 2 parts that are concept, and then one question about solving math related to that concept. There's currently, I think, 11 questions on the test total. Or is it 12? 11 or 12. And again, mixture of concept-based short answer and math using your formula sheet. And if you can do these, then you will be fine on the test, but I want to point out this little blurb at the top here. It's okay if it's a little fuzzy from the back row, I'll read it out loud. Note, I make my extra practice questions harder than the actual test. I'd rather you make mistakes on these than on the actual test. For example, on this list of practice questions, I have written out here several concept questions that just ask you flat out, what is this, write it in your own words. This is for the purpose of review, really, making sure that you understand the concept and can recall it, and then you can check against the answer key that I'm posting this afternoon. On the actual test, my concept questions are a lot closer to one-word answers, because I want you to be able to do them quickly. I might ask you something about this situation, yes or no, or tell me the name of this thing that's going on, something that fits on one line. Again, these ones are structured more like a response where you'd write a whole sentence, just again, for the purposes of review. A good example of that is right here, list Newton's 3 laws of motion. On the actual test, kind of like on one of the labs that I've been saying this throughout the whole semester. On the actual test, you have to pick the laws of motion out of 5 statements and number them correctly. Here, the harder version is writing them from memory. But if you can write them from memory here, you can pick them out of the lineup on the actual test. Does that kind of answer the question? Okay. So if you can do the homework and you can do these practice questions, you'll be good on the test. And I specifically wrote the test given the sorts of things that are on the homework. Some of the test questions literally are ripped straight from the homework or are slightly tweaked versions of it. And furthermore, I then wrote all the practice questions after the test to make sure that all the concepts in math matches. It's not the same questions, but if you can do these, you can do those. Sound good? I got a little off topic there. Does that, again, answer your question?
Yes, sir.
Okay.
Thank you.
I'll be posting an answer key for this afternoon. So again, this is a great thing to study over the weekend on Monday, and we'll be able to cover it together. Any questions related to it in lecture next week prior to you taking the test? Anything else on your minds right now? Yes.
We get a formula sheet, right?
You do. I have posted an updated class formula sheet within the Introductions and Resources tab. So right there, Phys equation sheet. This is my current draft of the more updated version, changing the formatting, moved a few things around. It's still not perfect, however, because there's a few more equations I need to add that I didn't get to this week, but those are from the other half of this course. Every equation that you need for this test is here.
So just print that out and bring it.
Yes, and even if you don't print it out and bring it, I will have several for you. So you don't have to, if you don't bring one, you will have one available to you. The test is written for you to have this. You also, again, if I haven't said it recently, need a calculator that is not your computer or cell phone. It doesn't have to be a fancy one, but it does have to be able to handle square roots. Like squared and then separately square root. So you'll absolutely have a formula sheet. And you can write on it. You can like label things, put King Henry died by drinking chocolate milk at the top of it. You just can't write the laws of motion. You can't write worked practice problems.
So that's the only formula sheet you can have, you can't make our own.
I've had students ask if they can make their own. I'm not opposed, but I would have to look at it first. I'm not opposed though. Yes.
For the Tuesday one, will it be you or Mr. Edwards?
It will be Mr. Edwards. I have given him the instructions for how I want the test proctored. He's been proctoring tests for me for a couple semesters now. And the thing that either he or I are here to do during the test is encourage you to ask questions, make absolutely certain everything on the test is clear to you, make sure you know what's being asked, and I think that was it actually. I felt like I had a point, I lost it. Whether it's him or me, my goal is for you to make sure you understand what the question wants of you, even if the way you need to hear it isn't what's written there. And in case, you shouldn't need any extra conversions on there, but if anything comes up, that's why one of us is here. So I want you to ask questions, whether it's me or Dr. Edwards, and we will help you as much as we can. Does that answer the question? Okay. Anything else on your minds right now? All right. In that case, first thing I want to do is just review a couple of things, bless you, from the end of chapter 7, just to make sure that the concepts sink in before the test. The last concept we talked about is that of work, the idea that whenever you exert force to make something move, you are using up your own energy, you are using it, transforming it, and transferring it between objects. And that is, anytime energy is used, transferred, or transformed, something did work to do so. Work is the mechanism through which energy is used, transferred, and transformed. The formula for work we've discussed is work equals force times displacement. Basically, if you push on something and you make it move, you are doing work, you are using up energy and giving it to whatever you are working on. And so the W there, W is work. You can think of it as the amount of energy needed to perform the task, the amount of energy that is given to whatever is being worked upon. And the only restriction with this formula is that parallel symbol, the force and the displacement have to be parallel to each other. If I push something to the right and it moves to the right, I am the one doing that work. If I push something to the right and it moves up, odds are something else is doing that. And it's the thing doing work, I'm not accomplishing anything. So, quick practice problem, just I'm going to give this one to you guys to work amongst yourselves for a minute. An athlete is going to deadlift 75 kilograms, which again, for your sense of scale, is a lot. Lifting the weight a total height of 2 meters from the floor. So starts on the floor, elevates up to 2 meters up here. Two things I'd like you to tell me. First, how much work is required to lift this mass? And then second, how much GPE does the weight gain as it rises from the floor up to that height? Answers so far? almost. Almost. Sorry. What I mean by almost, what is the formula for work? Alright, force times distance. I'm going to write delta y instead of delta x just because the object is going up in the y-axis instead of the x-axis. Now in order to lift something, you do have to exert force on it. How much force is it going to take to lift a 75 kilogram item? When you lift anything, how much force does it take to lift it? What value is the required force to lift something equal to, or equal and opposite to?
As much as it weighs.
Sorry?
As much as it weighs.
As much as it weighs. If it weighs 10 newtons down, you have to exert 10 newtons up at minimum to overpower gravity and start moving it upwards, right? So, whenever you're lifting anything, the required force is, at the very least, equal to and opposite the weight of the item. So to find the force we need to lift with, we need to find the weight of 75 kilograms. How do you find the weight of anything?
Multiply it by gravity.
Specifically, which number related to gravity? Very good. But yes, mass times the acceleration of gravity is the weight of an item on planet Earth. So the weight of this 75 kilogram item would be its 75 kilogram mass. We want it in kilograms, but it's already in kilograms, times the acceleration of gravity of 10. So this object weighs 750 newtons, and that means you have to use at least 750 newtons of force to lift it. You need that much to at least equal gravity, and then you can begin moving the item upwards. So that's the force that we need. That's the force that's going to go in for force parallel. We're going to lift it 2 meters, and both the force and the displacement are parallel. They both point up, so that's not an issue here, thankfully. And so you will get a final answer of 10 times 150, 1,500. And what is the answer for work? Sorry, what is the unit for work? Joules, very good, because it's the amount of energy used, therefore it has the same unit as energy. So, 1,500 joules to lift this particular object. I think real quick. I'm doing a quick, calculating an analogy real fast. That burns about 2 calories. Factoring in the efficiency of the human body. We'll talk about that later. So, how much GPE does the item gain when you lift it to that height? What's the formula for GPE?
Times gravity times height.
Yep. MGH. So we're going to take the mass of 75, multiply it by 10, multiply it by 2 meters, and wait a minute. Does that look familiar? We literally multiplied all the same numbers by each other. mg is the weight, 75 times 10, and then that times 2 is 1,500. When you lift something, the work you're doing is using up your own energy to give the object in question its GPE. This ties back to conservation of energy from Wednesday. If the item gains this much energy, it had to come from somewhere, in which case it came from your muscles, the work you did on it to give it that energy. And you got that energy from your breakfast. So, they're the same on purpose. Lift anything and the work you do is equal to the energy, the GPE increase of the object. Sound good? All right. So, things to remember just from this one. To lift anything, the force up has to at least be equal to the weight. So if I ask you to calculate the work done lifting something, the force, you should calculate the weight and use that. The upward version of that as the force. And energy is conserved. It is not spontaneously created or destroyed. That is the last concept from chapter 7 that is on this test. There's a few more things we'll cover after the test, but I don't want to be giving you new things all the way up until it. So everything else from chapter 7 we will cover later. Which means now I plan to just look over all the test review stuff, make sure that you have heard from me what things you need to be able to do before the test. Any particular questions, namely from the whole of chapter 7, before switching gears? All right. Oh, tab. All right. Looking at the Test 1 tab, chapters 1 through 7, the tab itself has a list of everything you need to be able to do, all the concepts you should be able to recognize, and I want to go through them. So again, you've heard from me all the things you need to know prior to taking the test. First pieces of math we were doing related to units. You want to make sure that you can convert units. I do believe that the way I wrote this test, the only conversions required are metric prefix conversions. So say I give you something in grams, you do have to tell me how many kilograms that is before you can use it in any of your other formulas. As a quick practice question, how many kilograms is 10 grams? 0.01. Someone said it. And the reason for that is grams are 1,000 times smaller. That is 3 decimal place jumps to the left. And the reverse is true going the other way. You multiply by 1,000 to go from kilograms to grams. You are allowed to write this on your formula sheet if you like using that to visually help you. Additionally, when I say units, I do want your answers to have units on them. Say again, I ask you to calculate the work required for a certain task. I want you to put joules on the answer. I don't put a lot of points for units. Out of a 10-point question, I might assign half a point to there being a unit on the end. Meaning you could still get an A and not write any of them, but it's still in your best interest to write them. The reason I grade to units is because NASA has lost millions of dollars of lander probe because someone's units were wrong. So if you were doing science professionally, you'd need to put your units, so you have to put your units. So make sure you know the unit of measure that we use in the metric system for all the different things you can calculate in this class. So when you're looking at this and you see units, you can check it off if you can do and understand all of that. Next, we started talking about the laws of motion. You, again, do need to be able to pick them out of a lineup and then use them. I have them summarized here in their shortest possible forms. The full versions are both in the notes and will also be on the answer key to the practice questions. First law is the law of inertia. That's the law that says object at rest stays at rest, object in motion stays in motion until acted upon by an outside force. Again, summarized by the concept of inertia. Second law is net force equals ma. I wasn't able to get the sigma symbol into this particular thing. And that's the one that says that if the net force is not zero, the object will begin accelerating. If the net force is zero, there is no acceleration. Related to that, you do have to be able to calculate the net force acting on an object. For example, what is the net force acting on this box? 100 newtons to the right, 75 newtons to the left. Why don't you say it? I heard you mutter it.
25 newtons.
To the right, very good. So, when it comes to net force, make sure that you can calculate it, use it in this formula, and do note that vector directions are important. The net force on this is not 175 because they're working against each other. It is 25 to the right. And lastly, third law, the law of action and reaction. If there is an for every action force, there's an equal and opposite reaction force. You will have to be able to identify a small amount of third law pairs on the test. Biggest thing that I would ask you to be able to remember about that, this is 1 kilogram. What two forces are currently acting on this item?
Gravity and normal force.
Gravity down, normal force up. Very good. Are those two things third law pairs? No. Why are gravity and normal force not third law pairs? There's at least two reasons. Told you that they weren't. Why are they not?
Nothing happens.
That's part of it. You're actually right. Nothing happens as a result of this. That's because that stems from one of the reasons. It's that both forces are acting on the same item. The way that the third law pairs always work, they can be described as if A acts on B, then B will act back on A. It's always a complete switch of source and target. Meaning that the two forces don't act on the same item. This first force acts on item B, the second force acts on item A. Two different targets. These two forces are acting on the same target. They cannot be action-reaction pairs for that reason. These follow the pattern of, if Earth's gravity pulls down on this mass, the table pushes up on this mass, which would be if A on B, then C on B. The mass is the item and the table is a third item. If the first item is the Earth and the second item is the weight, the table is item 3, item C. That doesn't follow this pattern. Third law pairs are always A on B, B on A. So that is one reason. The other less common reason is that gravity and normal force are not by definition equal nor opposite. There are cases where normal force is not the same number as gravity, nor in the opposite direction as gravity. If you set something on a ramp, normal force tilts because normal force has to be perpendicular to the ramp's surface. They're not opposite, they're not third law pairs. Likewise, they are not always equal either, because if I push down on this weight, its actual weight does not change, but the normal force still has to increase to overcome the added extra force I'm applying. So again, they are not always equal nor opposite, and they both act on the same target rather than different ones. Make sense? Okay. In that case, what are the third law pairs to this force of gravity and this normal force? We'll start with gravity. If the Earth's gravity pulls down on the mass, then what?
Mass's gravity pulls up on the Earth.
Very good. The third law pair to gravity is always more gravity. If Earth's gravity is affecting you, your gravity is affecting the Earth. In that case, the action-reaction pair to normal force, if the table pushes up on the mass, then what's the opposite of that?
The mass pushes down on the table.
The mass pushes down on the table. The table doesn't care if gravity is the reason why, the table just cares that something's pushing it. It doesn't care if gravity is the reason. And that's similarly why if I just push down on the table, gravity doesn't have to be a factor. I'm just adding force and the table will respond. So the opposite to normal force is just the two surfaces interacting even if gravity is not a factor. So if the table pushes up on the mass and the mass pushes down on the table does not know or care if gravity is involved. So when I say Newton's third law, you have to remember the law and be able to apply it to that extent, at least a little bit. Any questions before moving on down the list? All right, next up, equilibrium. You need to be able to identify if something is in an equilibrium state. What is the main identification for if something is in an equilibrium state?
Everything adds up to zero.
All of the, what specific thing adds up to zero?
Like the forces.
Very good. If net force is zero, then equilibrium. So, if the net force is zero, you know the object is in the equilibrium state. It's in a state of balance, nothing is pushing or pulling it in any direction. Now, a consequence of the equilibrium state, which you can also use to identify it, is if the acceleration of the item is zero, that is also indicative of an equilibrium state. Because according to Newton's second law, if net force is zero, no accelerating is going to happen. So, and then back to Newton's first law, if the object is not moving at all and remains that way, or if it is moving at constant velocity, that's not accelerating, therefore those count as equilibrium states. You have to be able to identify those. Related question, is falling an equilibrium state? No, very good. That's because falling is by definition an acceleration. You're accelerating at 10 meters per second squared, therefore falling is not equilibrium. Flying might be, but falling is not. Speaking of acceleration, 1D motion, all three of displacement, velocity, and acceleration. What I mean by these is be able to identify each of those terms when they're given to you in a question, and you should also be able to use, looking at the formula sheet real quick, this set of 4 formulas to describe the motion of items, both in terms of their displacement, their velocity, and their acceleration. So review these 4 formulas, make sure that you understand what terms are in them and that you can utilize them when describing motion. There are practice questions for that in the homework and on the practice test. I mentioned a second ago, acceleration of gravity. Remember, the gravity causes acceleration, and the value that we attribute to the acceleration of gravity on planet Earth is -10, meaning down, meters per second squared. I think I put lowercase g on the formula sheet. Pardon my muttering. Forces. We talked a bit about force already, namely net force. There are certain types of force you should be familiar with. We've already mentioned most of them today. Force of gravity, again, be able to calculate the weight of an item on planet Earth. Main thing to remember there, mass is not weight. If its mass is 10 kilograms, it's going to weigh 100 newtons. Bless you. Does mass change if you go to the moon? No, because mass is the number of protons, neutrons, electrons in your body. That doesn't change when you go to the moon. Does your weight change when you go to the moon? Very good, yes, it does. Because the moon has a different magnitude of gravity. So, mass and weight, different things. Normal force, again, remember it's a reaction force to a surface being pressed into. It is not the reaction force to gravity, but it is often opposite and equal to gravity, which is good if you're trying to sit in a chair. And lastly, friction. Things you should know about friction are that it always opposes motion, and it does not depend on speed. Your car speeding up does not increase the friction from the road or the friction that it experiences inside of its engine. Kinetic friction remains at a constant value. If kinetic friction pointing backwards is 60 newtons, and I'm pushing with 60 newtons forward, that's equilibrium, the item remains at constant speed. If I increase to 70 newtons forward, that's a net force of 10 newtons forward. The friction doesn't change because kinetic friction can't change. The item will begin speeding up. That's what happens when you hit the gas in your car. If you're speeding up, you have overpowered friction because it only has a certain maximum. Force-related questions? All right. Last 2 chapters that are present here. Last week we looked at momentum, which again is rho equals m times v. Impulse, change in momentum. Conservation of momentum, referring to this on your formula sheet. The notion that, like energy, momentum cannot be destroyed. The total amount that exists before a collision will remain after the collision, even if it is distributed differently between the 2 items. Remember, again, in lab, if something's approaching very fast and it hits a stationary item, they will share the momentum and once combined have a slower overall speed. This ties into, again, collisions. We tend to use the conservation of momentum formula to study collisions and how momentum is conserved in those collisions. And then the stuff from this week, we looked at two different forms of energy, KE and GPE, be able to identify and calculate those. If something is moving, it has KE. If something is at height, not zero, it has GPE. Conservation of energy states energy is not created or destroyed, it just transforms. So an object's energy level, total level, remains constant even if it changes states. An example would be an object that you throw into the air, KE turns into GPE on the way up, and then KE again on the way back down. And lastly, work. You do work, you use energy, you give it to something else. Also subject to the conservation of energy. If you do 500 joules of work, you lose 500 joules of your own energy and give it in some form to whatever you were working on, like the deadlifting the weights example from earlier. And that is every concept present on the test. If you use this like a checklist and can do all the practice questions, you will be golden. How you guys feel? All right. Any questions, concerns, etc.? All right. It's Friday. I've been talking at you for a while, so unless there's anything on your mind, serious or not serious, we can start packing it in for the day. Any last thoughts or things you need before the weekend? All right, in that case, as you're reviewing, please let me know if you have any questions. The homework all has answer keys already posted. I'll be further adding an answer key for the practice question, the additional test practice question this afternoon. Please have a great day and weekend. Get some rest.